Good morning, everyone. This is Preeti Shinde presenting this webinar for pH electrode maintenance and many other things that should be taken care of regarding selecting a pH electrode and maintaining it. I hope I am audible to everyone. Firstly, I would like to thank you all for giving your valuable time for this webinar. HANNA instruments have always been innovative when it comes to the need and age of analysis, right from basic to the most complex analysis. Out of this, pH is the simplest yet critical qualitative measurement each and every analyst has to do in its everyday analysis. It is always been very critical as one need to have pH reading accurate as per the measurements and analysis are dependent upon this. The pH electrode is always the key to the age of pH measurement. One has to dip the electrode in the sample and note down the measurement. But question arises when the readings are not stable or are not accurate or are totally unexpected. Then the question comes: Is my electrode working fine, or is my meter have a fault, or my buffer or my sample is wrong? So today we are going to discuss the working of pH electrode, the sale potential, and what are the factors that affect the working of pH electrode, and many more facts that users should know before we start using pH electrode. You may know, I know most of you have of time. More information, more information to your knowledge base. But of course, we will have a question and answer session after the webinar. So before going towards maintenance, first we will see working of a pH electrode. As you can see on your screen, a pH electrode consists of a sensing bulb, a sensing wire, a sensing electrolyte, reference electrolyte, and a reference ceramic junction. The sensing bulb, sensing wire, and sensing electrolyte are responsive to the hydrogen ion activity present in the solution and gives out variable millivolt as a result of response to the hydrogen ion activity, whereas the reference electrolyte are responsible to give out stable voltage. This reference electrode is in contact with the sample through ceramic junction. The pores in the ceramic junction allow the reference electrolyte to flow out of the electrode in a steady speed. Other than these components, there are other than these components, there are outer hydrated layers, inner hydrated layer as a part of cell potential. In acidic solution, H plus ions diffuse in the outer hydrated layer and a positive charge is established. Whereas in alkaline solution, H ions diffuse out of the hydrated layer and give a negative charge. Thus, this is the way how electrode identifies whether a solution is alkaline or basic. If a solution is alkaline, negative charge is developed or you get negative millivolts, and if the solution is acidic, you get positive millivolts. These hydrated layers limit the diffusion of hydrogen ions according to the pH of the solution. If there is any disturbance in these two hydrated layers, the user might observe fluctuation in the readings. Conventional electrodes were normally single junction, as depicted in the figure. These electrodes have only single junction, which serve to put the reference electrode system in contact with the sample. Under adverse conditions like high temperature, high pressure, highly alkaline or acidic solution, highly contaminated solution, there might be possibility to have a positive flow of sample in the junction through the junction in the electrolyte, and often ingress of sample into the reference compartment contaminating the reference electrolyte. If this is left unchecked, the reference electrode can become contaminated, leading to complete electrode failure. Another potential problem with single junction electrode is clogging of the junction due to AgCl precipitation. AgCl being less soluble in the sample than the reference electrolyte, solution precipitates in the reference compartment. To overcome all these issues, the reference electrode was well jacketed in the inner ceramic junction and, and the reference electrolyte was made silver free to avoid the precipitation. Thus, if there is any contamination of reference electrolyte, one can easily refill the electrode and start using electrode again. The confining silver content electrolyte in the internal junction minimizes the possibility of reference contamination. The outer ceramic junction is porous substance which allows the electrolyte to flow out of the electrode with a constant speed. This similar flow rate is not always suitable to all types of samples. Sometimes in low conductive samples, the ceramic junction electrode will not give fast response, or as well as ceramic junction is susceptible to get clogged in highly contaminated samples, and due to this fixed flow rate there here you need to have different types of junctions. So as you can see on your screen, there are these are the different types of junction that we at HANNA offer. First is single ceramic junction. These junctions are responsible for response of pH electrode. A single ceramic junction is used for general purpose uses for samples such as the samples that have high conductivity but low contamination. Whereas a triple junction electrode means there will be three ceramic junctions on the outer side of the electrode are used in low con- sorry are used in low conductive samples, giving out high flow rate and stable readings in low conductive samples. Even though if you are using a triple ceramic junction electrode in low conductive sample, you need to give electrodes specific amount of time to get stable reading. Oh, and next is the cloth junction. An acceptable cloth junction is replenishable type. When electrode response becomes sluggish and eventually impossible to calibrate, one can easily renew by using an ordinary pair of scissors to simply pull out a small portion of fiber junction and you will literally have a reconditioned pH electrode. Another types of junctions we have are sleeve junction, open junction and PTFE junction. The sleeve junction and open junction electrodes are used where the clogging of junction is most susceptible. In open junction electrode, a reference electrolyte is in direct contact with the sample, thus high flow rate and fast response giving. And sleeve junction electrode is used in samples that have high solid content and can easily remove the clog of junction. This is said to be a CPS technology. CPS means clogging prevention system technology. This utilizes the porousness of ground glass coupled with a PTFE sleeve to prevent clogging of the junction. The ground glass allows proper flow of liquid while the PTFE sleeve repels the solid. As a result, pH electrodes with CPS technology takes up to 20 times longer to be fouled as compared to conventional electrodes. Even if the sleeve junction gets clogged, you can just easily pull up the sleeve of the electrode on the upper side of the electrode and clean the uh, clogging. But it is rarely necessary. Cleaning solutions will do the work efficiently. Similar is the PTFE junction electrodes, which are used in process online or inline, as where one needs to have an electrode that is more chemical resistant and prevents fouling for continuous use. Even after such a fortified design of an electrode with all these types of junctions, what are the other factors that affect the working of pH electrode? So let's accept that the life of a pH electrode is very short. It does not last forever. The factors that affect the working of pH electrode can be high temperatures, or cleaning processes, or storage, clogging of the junction, contamination of reference electrolyte. All these factors go hand in hand. The factor that affect the working of pH electrode can be high temperature. Continuous monitoring at high temperatures can reduce the life to almost one-fourth of the expected than operated at ambient temperature. If you are continuously using an electrode for at 80 degrees or 90 degrees, you will hardly be able to utilize the life of the electrode up to 1 month only. After 1 month, the electrode will start giving errors or erratic readings that you cannot identify the exact reason. Then, foul cleaning process. Most common cause of inaccurate measurement is a dirty or improperly cleaned electrode. Remember, just because an electrode looks clean does not mean it is. This is important because during calibration, instrument assumes that electrode is clean. Just cleaning by water is not enough. Time to time, one has to clean electrode with cleaning solution to clear the depositions formed due to some samples or the contaminants in the samples, which are not visible to normal eye. Foul storing practices also affect the working of pH electrode. Storing pH electrode in distilled water is the biggest misconception people have. By storing pH electrode in the distilled water will result in the leaching of glass, also the leaching of salt from the reference electrolyte into the distilled water, as distilled water is a very aggressive solvent. It is just like storing a pH fountain pen upright and eventually stops working. Storing without any storage solution will dry out your electrode, resulting into high errors in readings at the outer hydrated layer are not present. Similarly, clogged junction and foul cleaning processes go hand in hand. As a foul cleaning or no cleaning practices lead to clogged junction, ahead to sluggish readings, and very slow response, as there is no space for electrolyte to come in contact with the sample and hence lowering the electrode performance. Contamination of reference electrolyte solution takes place as the solution being measured is allowed to migrate through the junction, entering the electrolyte cavity, thereby changing its composition and altering the electrochemical reaction completely. Then one should one then how one could understand that after all these precautionary practices, if the pH electrode is working fine or not, is in good condition or not. Thus, the answer for this is calibration. Calibration is a demonstration that an instrument produces results within specified limits when compared to known standards. Specifically, calibration is performed to compensate the changes in potential within the measuring and reference electrodes as well as change in potential between them. pH probes are not perfect, therefore they must be calibrated. Calibration tries to compensate any deviation due to sample attack, due to storage processes, due to cleaning processes, or due to maintenance processes. Any deviation from these processes from its ideal behavior. It teaches the instrument to yield accurate results when tested with unknown values. Calibration of instrument is a very critical activity. Hence, it is done with the solution having known pH. All equipment should be calibrated with NIST traceable standards to guarantee the readings can be trusted. Following is the process one should follow when calibrating your pH electrode. Using rinse solution and final solution separately will minimize the error due to actual buffers and thus leading to the accurate calibration. Starting from rinse, then to the actual solution and then calibrating. As calibration is an important process, there are some precautions each and every user should know. Always leave the electrode just above the junction. It helps the reference electrode to come in contact with the sample and complete it to potentiometric sale. Wash the electrode and never ever wipe the electrode in reading samples or buffers. Washing prevents the contamination of samples or buffers with earlier samples or buffers. Wiping the pH electrode can disturb the outer hydrated layer and thus disturbing the diffusion of hydrogen ions in and out of the layer. Never dip the electrode directly in the water. It can lead to contaminate the stock solution if there is any deposition on the electrode. Thus, always pour a representative buffer or sample and then take the measurement. Also, make sure that the meter is in ATC mode and the temperatures of all the buffers are similar. People many times ask when should you calibrate the meter or what should be the frequency of calibration. And one thing is everyone should understand that we calibrate electrode and not the meter. Meter have all the algorithms set in its circuit and the calibration of the electrode is necessary as the electrode being a mechanical part that senses the activity in terms of millivolt and then these readings are converted into pH readings. Also, the pH electrode is the mechanical part that comes in contact with the sample, takes the attack of the sample, also the temperature and other changes due to the sample that that occur in the sample and that affect the working of the electrode. Thus, electrode should sense proper millivolts. Hence, electrode is the thing that is to be calibrated, not the meter. We always advise our customers that calibrate just before starting your measurement. And after ending your measurement, thus you will understand if there is any drop in slope or offset due to sample reaction in the electrode. Other than this, one could calibrate before and after critical measurement that we need to yield high accurate results. Calibrate when you think that their readings are not accurate or suspect any errors in the meter or sample or electrode. Calibration is necessary when readings appear erratic. Thus, calibration is the key to yield accurate results. But what if you don't calibrate? If you don't calibrate your electrode? If you don't calibrate your electrode, the errors due to many factors will contribute to your reading. It might be due to deposition or due to dried pH electrode. The millivolt generation by the deposition on the electrode will add on to the millivolts of the buffers or samples, thus leading to higher reading. Other than this, errors like acid error or alkali errors will remain completely unidentified. Most important factor, most important thing each and every user should take into consideration that calibration is never done for the comparison of two different meters. Instruments should be although all the instruments are tested with similar standards because each and every electrode is different and the response is also different. So how to detect potential error? Whether the error is in meter or is in electrode or is in buffer. The key to determine error due to calibration is the millivolt. of each calibration point. Each and every known standard buffer generates particular millivolt. Any change in these millivolts will make you understand the potential error. If the millivolt generated in the offset have large difference, then acceptance window and is carried on to the slope values as well, then there is a deposition on the electrode. If the difference between the pH unit is high, then check your buffers and many more. Also, keep a note of slope and offset values every time you calibrate your electrode. Also, and you should always note down the millivolt changes of all the stock buffer solutions at the time of opening it and gradually as you use it. You will understand when your buffer should be discarded and should be stopped and should not be used for calibration. Always note down the last millivolts of buffers to track the status of the buffer. Now, storing the pH electrode is an essential practice. Always store your pH electrode in a storage solution, thus aiding hydration of the electrode and the junction. After any cleaning procedure, rinse the electrode thoroughly with purified water and soak the electrode in the storage solution for at least 1 hour. Storage solution halts the leaching of ions from the ceramic junction. It hydrates the electrode bulk and establishes the gel layer and hydrates the junctions also. When you try to calibrate your electrode, there are only three things that can cause error: a meter, electrode, and buffer. Each and every pH buffer has fixed millivolt readings according to the pH. Hence, we know which buffer can can produce how many millivolts. Thus, in any case, if your buffer is not showing pH that are not expected, just calculate the millivolts and you will understand where the exact issue is. And thus, using NIS-free traceable buffers can give you the surety of the same. These buffers are prepared in the standard solution under controlled environment with air grade chemicals and calibrated under air grade chemicals, calibrated A glassware for A class glassware, thus minimizing the errors in the calibration. Also, these buffers, the NIC traceable buffers, have high buffering capacity. Thus, in any case, if buffer gets contaminated, still the millivolt reading might not exceed the acceptance criteria, thus minimizing the errors in calibration. And these values can be trusted. Using certified buffers having long validity and are stable, thus minimizing the skill to prepare in-house buffers. At this note, I would like to thank you for attending the webinar. Please feel free to contact me or mail me for any queries. If you have any queries, you can able to mail me as well on my email ID mentioned on the right bottom of my slide. Thank you.